Today I will show you how to solve this particular integral. We will learn how to use differential equations and infinite series to solve integrals like this. We shall first define two different series and we will use them in our calculations to make the differential equation. Why are these series related? We shall get to know that very soon. To understand, we first look at this demonstration. If you start with e to the power ix and then use Euler's formula repeatedly, first of all, you get e to the power ix is cos x plus I sin x. Well, now you can obviously break the exponential into two different parts. You take e to the power cos x and you take e to the power I sin x. Now, again, of course, since this is in the form of e to the power I theta, I can again write it as follows. So this becomes cos of sin x plus I into sin of sin x. Now, if you break it down by multiplying them, you simply get the first term as e to the power cos x multiplied by cos of sin x plus an imaginary term. But if you notice, the first term is exactly our integrand. This would mean that if I were to write the real part of e to the power ix is nothing but our integrand, which is e to the power cos x multiplied by cos of sin x. This helps us because we also know that the exponential function has a Taylor series representation. Since we know that e to the power x is nothing but summation n equals to 0 to infinity x to the power n divided by n factorial. This helps us understand that if we were to replace x by e to the power ix, we would also do the same on the right hand side, and this would become n from 0 to infinity e to the power I nx by n factorial. And now, since we already know about the Euler's formula, we can again write this as n equals to 0 to infinity, and we can replace this with two different infinite series cos nx by n factorial plus I times n equals to 0 to infinity sine of nx by n factorial. And of course, the real part from this definition of e to the power of e to the power of ix simply comes out to be summation of n equals to 0 to infinity cos of nx divided by n factorial. Now you can equate and you can understand why this is equal to this. We can obviously find out this in a different way using differential equations as well. But this is a much better way to simply find this out. But using real analysis only, we can do that using differential equations, which would be shown in the video now. So let's go back there. Now we understand what C of x and S of x are. So term by term differentiation, and this is valid because they are uniformly convergent. So once you do Cx, you get this following series. You can expand sine of k plus 1x using the given formula, and therefore you will get the following expression involving both S of x and C of x. You can repeat this procedure again with S of x, and we are going to get the following two equations. Now, C prime x becomes minus Sx cos x and minus Cx sin x, while S prime x becomes C of x cos x minus S of x sin x. Now, we understand we can basically now define the functions that we saw right there in our explanation. And using that, we can easily compute the value of the integral by equating it to the series. So we are basically proving here that first we are going to prove using uniqueness theorem that both the S of x, C of x and f of x, g of x have the same differential equation. Now you can see if you differentiate f dash x, you get the following result. And similarly, if we were to do g of x, we would get a similar result as follows, which is g prime x will be equal to minus fx cos x minus gx sin x. Similarly as f dash x. Now, when we check the initial values, because the uniqueness theorem demands that the initial values must also be the same, along with the differential equations, we see that they also match because c of 0 is e and s of 0 is 0. Similarly, as f of 0 is e and g of 0 is 0. This would imply that the uniqueness theorem holds and the solution to c of x and s of x must be the same as the solution to f of x and g of x. Now, finally, we are sure that the following function is basically the series representation, and we can plug it into an integral as follows. And now the process is not so hard because 0 to 2 pi cos of n x dx is not really a hard integral to deal with. We can simply check the values of this integral in for two different cases, n equals to 0 and n greater than 0. For the first case, we see it's basically 2 pi. For the second case, we see that this is nothing but a sine of nx by n from 2 pi to 0, and you can evaluate it, and that's going to be 0 as well. So if you were to actually expand it term by term and integrate, only the first term will survive because everything else is 0, and therefore making the value of the integral 2 pi. So the final answer for our integral is 2 pi. We saw two kinds of methods here. Hopefully, we did learn something from this, and I will continue to bring on such videos. Thank you for watching.